So, today we will start with the unit 4 of your syllabus on potentials and fields. Okay. Potentials, you all know, we all have been dealing with potentials in many ways in solving circuit theory or in electromagnetism also, but these potentials actually arise from electromagnetic equation. And now after doing so much in this course, we must have at least you must be accepting the fact that Maxwell's equations are the basis of all electromagnetic phenomenon. You take any phenomenon and we can explain it by using Maxwell's equations. Okay? And these Maxwell's equations in general are written as del dot E, second is del cross E minus del B by del T, and third is del dot B is equal to 0, and fourth is del cross B is equal to mu naught epsilon naught del E by del T plus mu 0. J is the displacement current. Okay. So, this we know, and I can see here, see this equation and this equation clearly indicates that these 4 set of equations are interdependent, they are interconnected equation. Okay. So, here it means B is changing, E is also changing, electric field is changing with time, and magnetic field is also changing with time. Okay. So, when I say that when we see that magnetic field and electric fields are changing with time, it means either current or charge or both are changing with time. If there is change in electric field, it means charge. From Coulomb's law, I know that if there are two separated charges, then by Coulomb's law I can calculate the electric field between these two charges because of these two charges, and if I have a current, then I can calculate the magnetic field. Okay. So, it means if my B is changing, E is changing, it means charge and currents are also changing with time. But if suppose I want to consider the case where all currents and charge are static, they are not changing with time. Okay. Currents and charges are static. So, when the moment I say that current and charge are static, static means they are not changing, they are fixed. So, it means this is 0, del B by del T is 0, and del E by del T is also 0. Okay. So, I get new set of equations . And I get del dot B is equal to 0, and fourth is del cross B is equal to mu 0 into J. These are 4 equations. Now, a very interesting fact comes forward that now these set of equations are independent. It means electricity and magnetism are independent phenomenon. They are not connected to each other. The moment I fix the charge and the current, the moment I say that my charge and current are fixed, they are not varying with time. These 4 set of equations, these Maxwell's equations, which were before interconnected, they were interdependent equation, they become independent. Now, you can see here. Okay. So, these 2 equations are the heart of electrostatics. These 2 equations are the heart of electrostatics, and these 2 equations are from magnetostatics. Okay. So, I can say here that in electrostatics, I know that B and E are vectors, magnetic field and electric fields are vectors. So, I can say that in electrostatics, the vector fields will have given divergence and 0 curl. In electrostatics, vector fields will have a given divergence, divergence is non-zero, given divergence and 0 curl. So, I can say here that given, or I can say non-zero divergence and 0 curl. Whereas, in magnetostatics the fields will have 0 divergence and non-zero curl. So, this is very important. These two conclusions that we derive from electrostatics and magnetostatics are extremely important, that in electrostatic a given field will have non-zero divergence, that divergence will not be 0. I can assume a charge, whether you take a positive charge or a negative charge, okay, that will have some electric fields of line coming out of it. Whether it is positive divergence or negative divergence, it will depend upon the property or the virtue of the charge, but there will be a divergence. But if charge is static, there is no curl, curl will be 0, because the field produced will be irrotational. Okay. But the moment I come here, because monopoles do not exist, magnetic charges do not exist, so divergence of B is 0. Okay. But because of these magnetic field, if there is a magnetic field, there can be a displacement current. Okay, there can be a displacement current. So, these are quite intuitive, these things are quite intuitive, they are not new, but now because we are looking at it very specifically, so it might seem new, but they are not new, we all have read about it, we all have implicitly learnt this. So, now it means we will start with electrostatics. We will start with electrostatics and then we will go to magnetostatics. So, if I want to start with electrostatics, I will first, what I will do is, in electrostatic, because I know current and charge are static, they are not going to change, they are not going to move. So, what I will do, I will assume a situation, where charge are completely specified. The location or the distribution of charges in a given space is completely specified. So, once this happens, then our life actually becomes very simple, or you can say it becomes trivial, because once you know the location of charge, then just directly by applying the Coulomb's law, you can calculate electric field, force, work done, anything you want you can calculate. You just need to know the Coulomb's law, and Coulomb's law says that if two charges are separated by a distance, say r, then the force between them is proportional to the product of the charges and is inversely proportional to the square of the distance between them. Okay. So, this is a very simple law. So, by applying this law, we can calculate any parameter for electrostatics. So, we will start with this situation, that my charges are completely specified. So, I am going to say that in a given space, location of charges are specified. So, actually it is a good thing for us if everything is specified. So, now what we want to take first? We will start with potential, electric potential. So, for this situation, I will try to calculate, or I will try to analyze the electric potential. Okay. So, once I have electric potential, by definition, what is electric potential by definition? It is the work done in carrying a charge in a given electric field from one place to the other. Okay. So, if you want, I can write here that by definition it is work done in carrying a charge in a given electric field, okay, from one point to other. Okay, the displacement is always like this. So, the traditional definition of work done is W is equal to, now if you are doing your work against the force, there must be a force, okay, then if the work is done against the field, then the work done is negative. If work is done along the field, then work done is positive. So, I assume that I am doing work against the field. So, I can write that this W is equal to F dot ds, or I will write dl, where dl is the displacement vector. Okay. This is the traditional definition of work done. W is equal to minus F dot dl, minus sign just because I am working in the direction opposite to the given field. Now, what kind of force field it is, I am not yet bothered. Okay. Now, I want to know, for me it is more interesting to know that how much work will be done in carrying a unit charge. Here we are talking about, I do not know how many charges are going to move from one place to other, but I am only interested in knowing that how much work will be done in carrying unit charge from one point to the other. Okay. So, the moment I write here, then this will be a work done in some different unit. Okay. It will not have the unit of joules now, because now it is work done on unit charge. Okay. Or what I mean is, I divide this whole expression by Q. Okay. So, I have some different unit is equal to minus E dot dl. Force on unit charge is electric field. Okay. Now, it is E dot dl, and I say that this is the work done. And if suppose I am moving from point A to point B, I am moving from point A to point B. Now, this is a path. I am integrating this electric field over a path from point A to point B. It means this integral is path dependent. This integral is path dependent. Is it clear? This integral, because it will depend that how we are going to move from A to B, isn't it? So, it will be very interesting. I mean, I can arrive at a very interesting situation that if suppose I have to move from A to B, point A to B, I move like this. Okay, I do some work against the force. So, I have spent some energy. Now, I want to get back that energy. So, what I do? I move on a longer path B to A, and I get back more than what I had put in. You can get back more energy than what you had spent. So, it is a very fantastic situation. If this equation is path dependent, then it means energy is governed by us. We can get as much as energy as we want just by having different path. You move on a longer path, you get back more energy. You move on a shorter path, you get back lesser energy. So, it means you will actually you will become reservoir of energy. Every time by choosing a longer and longer path, you can increase the energy content, but that is not possible, we know. I mean, you cannot change the energy content of any system. Okay. So, it means this is not possible. So, if I say that this is path dependent, then this, at least this example fails from what we have experienced till now, that the energy, you cannot change the content of energy of a system. It is always constant. That is the conservation of energy, right. So, it means either it should be independent of path, or if it is dependent on path, then there should be some restriction. Okay. So, now we will examine whether this is independent of path or it is dependent on path. So, for that, let me have a test charge Q, okay, and I have to take it from say point A to point B, right. I have to take it from point A to point B. So, now you see the electric field lines will be coming out of this charge like this, they will be coming out. Okay. Now I have to take this charge, or I have to move from point A to point B. This is point B. This is the direction of E here, and this is the direction of E there. Is it okay? Now if I have to move, then I will move like this. I will move like this. I have only one choice. I will move like this, and then I will move like this. So here is the path, okay, and work done is E dot dl. E dot dl. So now here you see electric field is in this direction, okay, and we are moving perpendicular to the direction of motion. So work done is, no, there is no work done. So I am going to work only along this direction. Okay. So it means again I am only concerned about the path from here to here. Okay. So it means this is actually WA minus WB. Now let us take a more complicated case. If suppose I have a situation like this. Okay, and I have to move from, say, from point A to point B. So how I will move? I will move like this, and I will come to an intermediate point A dash, then I will move above and I will come to another intermediate point A double dash, then I will move like this and I will come to another point, and then I will move here. Okay. So now you can see that along this path work done is 0. So actually my work is only dependent on this point and this point. It is independent of path. So we are only concerned about the end points. Okay. So I can say that work done is actually difference of two numbers. It's just the difference of two numbers, isn't it? I can say work done is a scalar quantity. So work done is just the difference of two numbers. So I can say that E dot dl minus A to B, E dot dl is equal to phi b minus phi a. I can say that E dot dl, phi is some number, some scalar field. Okay. So the value of this scalar field at point B and value of this scalar field at point A. I can say this. It is not dependent on this. I can take another example. This was a step movement if I have a smooth curve. Okay. If suppose I choose a reference point P naught, this is a reference point, and I always choose my path in such a way that I always go through the point P. Okay. If suppose this is point A and this is point B, and work done in going from P naught to A is phi A, and work done in moving from P naught to point B is phi B. Okay. Then I can say that work done in going from A to B, this is phi A, this is phi B, then work done in going from A to B is phi B minus phi A. Okay. I am moving on this path, E dot dl on this path from P0 to A. Okay. So actually this will be, this work done on this path will be E dot dl from P0 to A. Work done on this path will be, work done will be P0 to A. So that will be phi A minus phi P0. Okay. And work done on this will be phi B minus phi P0, and you subtract them. So you cancel them out and you have phi B minus phi A. This negative sign comes from here. Okay. So now you can see that, because now this reference point does not matter at all. This reference point does not have any significance. So, even if I do not have a reference point, even if I have a reference point, still my work done only depends upon the end points. Still my work done depends only on the work done. So, it means I can say that this E dot dl is actually just the difference of two numbers, and this number is called scalar potential field. This number is called scalar potential field. So, now what I do, I want to measure a small change in W. I want to measure, I know that W is equal to phi b minus phi a. Okay. Although these what are these? These are some coordinates in the space. So, it means this scalar field is actually position dependent. This scalar field is position dependent. The value of phi at b is different and value of phi at a is different. Otherwise, this work done would have been 0. Okay. So, phi b and phi a are some, this phi, the scalar field is position dependent. Now, I want to calculate small change in W if I move along x axis. So, I want to calculate delta W for a small change along x axis delta x. Okay. So, it means I can write that delta W, small change in W, is phi x plus delta x y z minus phi x y z. So, now my path is delta x. Is it okay? So, I can write this, that this is del phi by del x into delta x. I can call this, I can write this, right? Or I can write that delta W by delta x is equal to del phi by del x. Now, for E delta x going to 0, delta x going to 0, I can write that E is equal to, here I will have a negative sign also, E will be equal to gradient of phi from this equation. For delta x going to 0, I can write that electric field is equal to minus gradient of phi. What is phi? Phi is a scalar field. Phi is a scalar field. So, I am representing a vector field, I am representing a vector field as gradient of a scalar field, and this can happen only if and only if this field is irrotational. You can do this representation, that is, you can represent this vector field as gradient of a scalar field if and only if this E field is irrotational or curl of E is 0. This we know from basic mathematics. This representation holds true if and only if del cross E is equal to 0. Okay? But if you go back to your equations that we had written for electrostatics, we had already told that del cross E is 0, right. So, what we conclude and what we assumed are identical. Okay. So, it means I can say that these phi's are scalar potential fields, and every electric field can be represented if it is electrostatic. Only if charges and currents are fixed, then every electric field can be represented as gradient of a potential field, and this can happen only if the given vector field is irrotational. Okay. So, from here I get another conclusion that del cross E is equal to 0. Okay. Now, thing is, we know electric field. If I have charge, I can calculate electric field. Then why do I have to go define a new parameter phi? What is the advantage? We have done a lot of analysis, lot of mathematics, okay, to arrive at this conclusion, just to confirm and reconfirm this conclusion that everything is right. But why at all we need this phi? Why can't we just live with E? Can you tell me? बताइए. Can you think of some reason that why at all, long ago, why people wanted to add this term phi, the scalar potential field phi, why it was required? Why couldn't they live with E? Why couldn't they solve things with electric field? Why at all they needed potential difference? Any one of you? No? What is the basic difference between E and phi? Sorry, हाँ बताइए. E is a vector field and phi is a scalar field. So when I do E dot dl, whenever do I integration, I will have 3 integrals to calculate. Along, if I am in 3 dimension, I will have x, y, z. If I am in spherical coordinate system, I will have r, theta, phi. But because this is a scalar, it will have only one integral to calculate. So my calculation becomes easier 3-fold times. Okay? So just by 3 times you make things easier. That's why this phi came into existence. The scalar potential field came into existence. Once you know phi, very easily you can calculate E, because taking gradient of a scalar field is not difficult. You have to just operate an operator simply on a given field. That is not at all difficult. Okay? But calculating complex integral over complex volumes, complex surfaces is extremely difficult in different coordinate systems. So this was the reason. Now I want to tell you one last point for today's lecture, that always remember that if you have radial force lines are radial, okay, then this is a general statement. It is not true just for this case, it is a general statement. If your force lines are radial, then work done in that force field is independent of path. For any kind of force, if your force lines are radial, that is they are emerging out from a point or they are terminating at a point. Okay. So if your force lines are radial, then work done in such a field is independent of path. Okay. And there would always exist a potential for such fields. Whenever work done is independent of path, there will always be a potential, a scalar potential field will always be there. You can take the example of gravitation. In gravitation also we have gravitational potential, and there also force fields are radial. Coming out of a point object which is generally spherical in nature. Okay. So whenever you have this kind of force field, then work done, anywhere you move within this force field, work done is independent of path. You move on in any ways, if the end points are same, then work done is constant. Okay. So this was the last point for today's lecture. So in this unit we will be basically discussing about vector fields and scalar fields, vector potentials and scalar potentials. We will be only devoting most of the time on this, right. So that's all.